Howdy, students. So, you're going to do reactions, right? You want to make something. You're going to have two things usually that are going to go into it, maybe one thing, one reactant. Well, if you have multiple reactants that are going to come together to make another thing, you're always going to have one that limits you and one that is an excess, one extra bit. Let's learn how to work with those and really figure out some quantitatively how much you can make when you combine some things together. So, language, limiting reactants and percent yield. First, some terms. Limiting reactants are the reactant that limits the amount of product that is formed. That's an actual reactant that's going to come from the equation. Excess reactant is the reactant that does not limit the amount of product. It's in excess. You have extra. You have more than you need. It'll be left over. Theoretical yield is the maximum amount of product possible given the limiting reactant. So the theoretical yield and the limiting reactant are not the same thing. The limiting reactant determines the theoretical yield, but they're not exactly the same. And then actual yield is if you do the reaction, the actual amount of product that is produced is your actual yield. It's how much you actually made. And then we have the percent yield. That is how you compare the amount that you actually made to your theoretical yield. And ideally, they're going to be as close as possible. You want the percent yield to be as close to 100% as possible. And our formula for percent yield, just like all percent yields, is actual over theoretical times 100. So let's talk about how to solve them. So first, you're going to do the stoichiometry problem on each reactant to form mass. Again, unless otherwise told. You could say in liters or in moles, but usually you go to mass. And you're going to have more than one given, so you're going to have more than one problem that you have to set up. Then, the smaller amount of product that is formed is going to be the theoretical yield, because the small amount limits you. And then you label the reactant that gave you the theoretical yield as the limiting reactant. So here's an example, a fun example. Imagine Carly. Carly wants to serve ham and cheese sandwiches at her next party. It's a birthday party for her son. Her famous sandwiches need 2 slices each of ham, cheese, and bread. So what is the equation for the recipe? 2 ham plus 2 cheese plus 2 bread yields 1 sandwich. So Carly finds that she has 20 slices of bread, 40 slices of ham, and 40 slices of cheese. So, here's our question. What is her limiting reactant? Well, that's the bread, because remember there's only 20 slices. She's got 40 of everything else. What is her excess reactant? Well, these are actually, there's 2 of them here. She has excess ham and she has excess cheese, 40 of each. So, what is her theoretical yield? Well, if you need 2 of each of them for all of them, and she has 20 slices, that means her theoretical yield, she could make 10 sandwiches. But let's say her husband Bill comes along and eats 3 slices of bread. Now what's her new actual yield? Well, she can no longer make those 10 sandwiches. She can only make 8 sandwiches because she doesn't have enough to make that extra one. So that's the actual yield. So final term, what is our percent yield? That is 80%. It's 8 sandwiches, the actual amount that was made, divided by 10 sandwiches times 100, which equals 80%. And actual yield is usually not because somebody ate a reactant. It's usually it didn't fully mix. It didn't mix all the way down at the atomic level. Some other error came into account. But let's do another problem. Real problem. So you're going to determine the limiting reactant and the percent yield for the following. The equation: nitrogen plus hydrogen yields ammonia. And you'll note it's balanced. You have 1 mole of nitrogen plus 3 moles of hydrogen yields 2 moles of ammonia, NH3. So imagine you have 14.0 grams of nitrogen that reacts with 3.5 grams of hydrogens to give an actual yield of 14.5 grams of NH3. Now, this might look like there are 3 givens, but in reality, you have 2 givens for one problem and another given for another problem. Remember, a percent yield is going to use actual yield, so we know that this is not the given for the problem. What are the givens are 2 things that are reacted together. Anytime you see reacted, these are the reacted together. So these are our 2 givens. So we have 14 grams of nitrogen. We're doing a little bit of speed math here, but it's stoichiometry. You've been doing a lot of it. So 14 grams of nitrogen first into moles. That's the proper number. That's the proper molar mass. Then we have a ratio of 1 mole to 2 moles NH3 because we're converting to what we're producing, the actual ammonia. Then we have to go from moles of ammonia to grams of ammonia. Remember molar mass. So we get 17.0 grams of NH3. That is for nitrogen. However, we have a second given here, second reactant. So we have 3.15 grams of hydrogen here. We use our molar mass, 2.02 grams of hydrogen, 1 mole of H2. Then our ratio is now 3 moles of H2 to 2 moles of NH3. And again, we finish out by multiplying by the molar mass, 1 mole, molar mass. So now we have 17.7 grams of NH3. And you see where we're going here. What is going to be our theoretical yield? Well, we know that it's going to be 17.0 grams of NH3 because given the 14 grams, this is going to limit us. So again, you have to be careful. You have to go through the whole problem. You can't just go, this one has more, so it's going to make more, thusly the other ones are theoretical yield. This is our theoretical yield because it is the smallest one. It's the bread, just like the other ones. So what is now our limiting reactant or limiting reagent? Well, since this determined it, this theoretical yield, not 17.7, because that's excess, we know that we have N2 is going to be our limiting reactant. Nitrogens are limiting reactant. So now we determine our percent yield. Again, like I said, we have the actual yield. Hard to see here, but it's 14.5 grams of NH3. That is the given for a different problem. We know our formula is actual over theoretical. We get our theoretical from here. We get our 14.5 from the problem. So we have 14.5 grams of NH3 divided by 17.0 grams of NH3 times 100 gives us 85.3%. Second problem. Determine the limiting reactant, the theoretical yield, and percent yield of if 14.0 grams of nitrogen are mixed with, mixed is just like reacted with 9.0 grams of H2 and 16.1 grams of NH3 form. So if the form means it is produced, what do we know this to be? Yes, it is actually formed. This is our actual yield. So we know that is not our given. So we're going to worry about it later. But first, our equation, N2, 3H2, NH, 14.0 grams of N2. And we're trying to go to grams of NH3. Grams of NH3. We'll go long form here. N2. We know that the molar mass of N2 is 28.0 grams. That is equal to 1 mole of N2. In fact, I'll be good about it. We know we have 1 mole of N2 yields 2 moles of NH3. and 1 mole of NH3 is 17.03 grams NH3. We multiply that all out, just regular old stoichiometry. We get 14 times 2 times 17.03 divided by 28 equals 17.03. 17.0 grams. Yep, 17.0 grams of NH3. And then, don't mind that work. If we do 9 grams of H2, we have 9.0 grams H2. We have 2. 1 mole of H2, 3 moles of H2 to 2 moles of ammonia, 1 mole of NH3 to 17.04 grams of NH3, and we get 51. So our limiting, our theoretical yield is, hard to see it here, 17.0. Don't mind this other calculation, something went awry. But our theoretical yield is 17.0 grams of NH3, meaning our limiting reactant is our N2. Percent yield is going to be 16.1 grams actual over 17.0 grams. This is all times 100. Throw that in my handy dandy calculator. Plug and chug. Divided by 17 gives us 16.1 divided by 17.0 gives us 94.7%. 94.7%. Better than the last time. So, I hope that this makes a little more sense. Do more practice. That's the best way to do it. Moodle's your friend. And I hope that was helpful.